All right, let's learn about how force, velocity, and energy is related to these oscillating systems. Okay. So, first of all, unless we're told otherwise, we're to assume that the mechanical energy in an oscillating system is going to be conserved. In other words, that all the forces acting are forces within the system that are conservative. And therefore, the energy of the system, the mechanical energy of the system, is never going to change. It's going to continually oscillate between potential energy and kinetic and potential and kinetic. So I have potential is going to swing here, and I'm going to have now here it comes, and now I have all kinetic, and then it's going to swing back up, and I have all potential, and it's just going to keep going back and forth and back and forth. Now, no real system does that, but that's what we're to assume unless we're told otherwise. And later on, we'll deal with what do you do when there's friction or some other non-conservative force acting on the system. Let's just start off with a spring oscillator, okay? So here's what we got. It's going back and forth. When it reaches its maximum displacement, let's just talk about what that means, okay? When it reaches its maximum displacement, first of all, it stopped moving because it's changing direction. So therefore, the velocity is zero. And if the velocity is zero, the kinetic energy of the system is zero. It has no kinetic energy at this point. All of its energy is stored in the spring as spring potential energy at this point when it's at maximum displacement. Now, if the spring is at its maximum stretch, that means the spring force has to be at its maximum because remember it's negative k delta x is equal to spring force. So since delta x is at its maximum, force is at its maximum. So even though its velocity is zero, the acceleration is at a maximum because F equals ma. So if force is at a maximum, then acceleration is at a maximum. It's a little counterintuitive, but if you think about it for a second, it does make sense. Now, what about when the oscillator passes back right there through the equilibrium point? So it was hard to capture it at equilibrium. I did my best. Okay. So as we're passing through equilibrium, it's moving at its maximum velocity. This is the fastest it's going to be going. So all of this energy is now in the form of kinetic energy. Kinetic energy is the entire ME of the system is at its maximum. But if I'm at the equilibrium point, that means the sum of the forces is equal to zero. There's no net force acting on it the moment it passes through equilibrium. Therefore, since F equals ma, if the sum of the forces is zero, the acceleration is zero. Now, at this point, too, the spring doesn't have any energy stored in it. And I can say, I would look at this, it looks like it got energy stored in it to me. But think about it this way. If I started with the system in this position, I just put my hand on it and I let it go here and I let go of it, would it begin to move? And the answer is no, it would not. There is no energy stored in the system at this point. When it is at equilibrium, it has no potential energy. It won't suddenly start moving. I'm just going to put this one in here so you could use it in your notes. I'm not going to talk about it right now. So let's just talk about a pendulum. Well, it's basically completely analogous, right? So it's going to swing back and forth between potential energy, kinetic, potential, kinetic. So let's talk about it when it's at maximum displacement from equilibrium point, okay? Now, when it's at maximum displacement, it is going to stop moving and change direction. So the velocity is zero. If the velocity is zero, then the kinetic energy is zero. If the kinetic energy is zero, that means all of the energy is in the form of potential energy, in this case, gravitational potential energy due to the height difference between here and here. Now, if at this point here, the net force on it, the restoring force is at its greatest amount, and since the force is at its greatest amount, that means the acceleration is its greatest amount. Again, it's a little bit counterintuitive, but at maximum displacement, the object is not moving, but the force is at its greatest amount, so the acceleration is at its greatest amount. Now let's watch what happens when it passes back through the equilibrium point. So as it swings back down and passes through equilibrium, what's going to be true? Well, at this point, it's moving as fast as it's ever going to move. So its velocity is at a maximum, which means its kinetic energy is a maximum. In fact, all of the energy in the system is now in the form of kinetic energy for that moment that it passes through there. Now, at this point here, if I just put the pendulum and took my hand away from it without pushing it or anything like that, it wouldn't begin to move. And that tells me that there's no potential energy stored in it. So at that moment, as you're at equilibrium, there's no potential energy present in it. You can say, well, I cut the string under fault, but that's not what we're talking about here. In this system, we're defining this low point as zero potential energy. Now, as it passes through, since the net force acting on it is zero, that means its acceleration is at zero. Again, counterintuitive. You're moving your fastest, but you're not accelerating. Now, let's look at this. This is something you're going to have to wrap your head around. So if we look at oscillating systems, be they pendulums or springs, and we look at the position of it over time, we're going to get the sinusoidal graph that looks like this, right? It looks like a sine graph or cosine graph, whatever, okay? And there's a lot of information that can be unpacked from that, and that's what I want to talk about right now. How do you look at this graph and extract the necessary information? And it's cool, and it's not that hard to do. So let's just think about it, okay? First of all, we've already talked in a previous screencast that if I know if I look at a graph here, I can tell what the period of oscillation is, right? So if I look between here and here, I'm going to see it's 0.8 seconds. Between here and here, it's 0.8 seconds, zero point 0.8 seconds, zero point 0.8 seconds. Between any two maxima or any two minima is 0.8. Well, between any two maximum displacements in the positive or negative direction, it's going to equal zero point 0.8 seconds. So I can tell the period just by looking at it. But now let's focus on this, the amplitude. So I can take the amplitude, which is the maximum displacement from equilibrium, which should be the same on both sides. And basically, amplitude tells me the potential energy of the system. So what I'm going to do with these graphs, I'm going to look here, and I'm going to use this information about maximum displacement in terms of position. And from that, I'm going to determine how much potential energy the system has here, because that's going to inform me as to how much kinetic energy it has when it gets to here, because all of this potential energy at this point will be turned to kinetic, back to potential, back to kinetic, back to potential, back to kinetic. So by measuring this displacement, I know the ME of the system, and that's very powerful. So let's just look at this here. So I have an oscillating system going back and forth. So here, this is the spring, if you can't tell. Okay, so here I'm at my maximum displacement. So all of the ME is in the form of potential energy at point A. So here's point A. I'm at maximum displacement. The object is not moving at this moment, but all of its energy is in the form of US. So I could take this displacement, that's the delta X of the spring. If I know the K of the spring, which I could find by looking at the period if I know the mass, and I could figure out what the potential energy of the system is, and therefore the ME of the system. Now it picks up speed and is passing through equilibrium. So its displacement at point B is 0. It doesn't have any spring potential energy anymore. So all of its energy in the form of kinetic energy, which is a little bit difficult to measure from one of these graphs, but I can infer it by determining the potential energy. And then as it passes through this, it moves on, slows down, and stops at point C for a moment. And at that point here, I'm at maximum displacement, so the energy has all gone back to being potential energy. Well, the same thing is true for a pendulum. Forgive me, I got these two reversed. I should have put this one here and this one here. Let's not worry about that. So at point A, I'm at maximum displacement. Okay, here I am, maximum displacement. Now, in truth, I might end up measuring that in degrees. All right, but I could use L minus L cosine theta to figure out potential energy. But the point is, all of the energy is in potential energy at this point. As it swings downward, all of the energy is in kinetic energy at this point. Now it's going to slow down as it goes back up the other side, and eventually it's going to stop at point C when it has its maximum displacement, and all of its mechanical energy is now converted to UG. Totally analogous between the spring and the spring and the pendulum. So to reiterate, at maximum displacement, what we've got is our maximum potential energy, be it US or UG, our maximum force, whether it's force S or force G, maximum acceleration. All of these are at a maximum here, and therefore the velocity is 0, so kinetic energy is 0. As it passes through equilibrium, the opposite is true. It has its maximum amount of kinetic energy, which will be equal to whatever the potential energy was here. It has its maximum velocity, but the restoring force at this point is 0, so the acceleration is 0, and potential energy is 0. Okay. Now, if I was to make a graph of something other than displacement, let's just say I was to use a force probe to measure this, or to measure acceleration somehow. Here's what I would find. I get the exact same graph, because if you think about it, at maximum, in this graph here, at t equals 0.5, it's at maximum displacement. Well, that means at t equals 0.5, I'm also at the maximum force. Now, this value here is going to be different from this value here. However, the maximum force that I get is going to be found at the same place where I get maximum displacement. And therefore, the maximum acceleration is going to occur at time t equals 0.5 as well. And at t equals 1, the displacement is 0. So at t equals 1, the force is 0. And at t equals 1, the acceleration is 0. So these graphs all look identical to each other. The only way in which they would be different is what's on the y-axis. But the shape of it, in terms of the time values, is going to be identical. But what about a velocity graph? So if I did a velocity graph, we're going to find velocity is out of phase with it, perfectly out of phase with it. In other words, at t equals 0.5, we have maximum displacement. Therefore, the object has stopped moving when it's getting ready to move the other way, so the velocity is 0. As it passes through equilibrium point at t equals 1 second, I now have reached my maximum velocity, in this case in the positive direction. Now, as it continues on downwards at t equals 1.5, it has reached its maximum displacement, so it's stopped moving one direction and starting another direction. So therefore, at t equals 1.5, the velocity is 0. And then as it moves backwards to t equals 2, I notice here the displacement is 0, so the velocity is a maximum. So now it's got its maximum velocity in the other direction. So we just see these, the period is the same. If I measure the period of this one here, I'm going to see it's equal to 2 seconds. So 1.5 to 3.5 is 2 seconds. So if I go from here, I go from 1 to 3, it's 2 seconds. It has the same period, it's just shifted. So we say they're out of phase with each other. If I did a graph of potential energy, however, things get a little bit trickier. And the reason is that the period is going to be halved. And here's why. At this point here, it's got its maximum potential energy. And at this point here, it has its maximum potential energy. Halfway through its oscillation, it goes from maximum potential energy to maximum potential energy. So therefore, instead of having a period of 2 seconds, I'm going to have a period of 1 second, right? And what I'm going to find is there's no negative values because there's no such thing as negative energy. So when it is at maximum displacement, let's see. I'm sorry. So when it is at equilibrium, it's going to have 0 potential energy. And when it's at maximum displacement, it's going to have maximum potential energy. And as it passes back through equilibrium, it has no potential energy. And so, but I see that it's going to have half the period because every time I reach a maxima, so does potential energy. A graph of kinetic energy would be just like the one for potential energy, except again, completely out of phase, shifted over. Now, remember, in our last one, we reached our minimas at 1 second, 2 seconds, and 3 seconds. I should be half a second off from that in this one. Oh, good, I drew it correctly. Okay, here's why. At this point here, displacement is at a maximum, so kinetic energy should be at a minimum, 0. So at t equals 1.5, it's 0. At 1, I have my maximum kinetic energy because the displacement is 0. So at 1, I have maximum potential energy. So you can see my period is 1 second rather than 2 seconds. It's the same thing because every time I pass through equilibrium, I'm at maximum kinetic energy. I just have a couple of problems that you could work through. I'm not going to do them now. They're just for you to look at when you're trying to wrap your head around this, taking notes. But let's just look at this last thing here. So because kinetic energy and potential energy are perfectly out of phase with each other, if I plot them together, and College Board likes to show you this because it's really cool. We'll do this in class ourselves. What we see is that the kinetic energy and the potential energy are completely out of phase with each other. So when potential reaches a maximum, kinetic reaches a minima, and vice versa. If I was to sum up the values of these two and plot it versus time, I would get this. It's so cool. The mechanical energy stays constant as potential energy and kinetic energy are constantly doing the opposite of each other. Hey, thanks for watching. Hope this wasn't too long.